dynamics. So, as I stated, we're going to be concentrating on the adaptive form algorithm. The adaptive form algorithm has a number of parameters which can be edited to adjust the outcome of the surface file. So the first option is the polygonal budget, and this can be set to fine budget or specified budget. Fine budget, which is the default, tells the algorithm to determine the optimal number of polygons for the surface. Specified budget tells the algorithm to generate a surface using no more than the number of polygons you specify. So it derives the best surface it can for the polygon budget. Iterations. This specifies the number of iterations in the deformation process, and this can be increased or decreased. If the ratio of the object voxels to the volume voxels is small, the number of iterations should be greater than 10. Cube size. This is a really important option in the surface extraction module. This determines the resolution of the resultant surface. A smaller cube size will generate a higher resolution surface with more polygons. However, this surface can look more blocky or voxelated. If data is noisy or has a large number of symmetric tolerances, increasing the cube size will accommodate this. The scale coordinates. This option, basically, if you're working with anisotropic or non-cubic data, this option will scale the surface coordinates back into the real-world space. And then under scale coordinates, we have an advanced option there, and this provides access to three additional options: time step, surface force, and spring constant. The time step controls the speed of the deformation process, which impacts the number of iterations required to produce a final surface. Surface force controls how well the surface conforms to changes in surface temperature, and spring constant controls how well the surface lies across flat areas. So these advanced options can be used as well as smoother surface. So if you do want to generate smoother surfaces, then you can increase the time step. Fewer iterations in the deformation process result in less detail in the surface. You can decrease the surface force. The polygons won't pull in to small crevices in the surface, and if you increase the spring constant, the surface will bridge small creases and crevices. Okay, so we've talked a lot about surface extractor and the surface extractor module, the process, and the options that are available. Let's put that into some context now by reviewing the entire surface generation process. So first of all, we'll demonstrate how to segment bone from a CT dataset, and then how to generate the surface for this bone. Okay, so I'm going to move over to Analyze now, and from my workspace I'm going to select this CT scan of the pelvis, and I'm going to do my initial segmentation using the volume render module, which is available from the display menu. So this dataset is actually anisotropic, so I'm going to adjust the scale up here so it appears anatomically correct when we render it. And I'm going to go to Generate, Threshold, and I'm going to set a threshold level that will allow us to see the bone. And I'll hit render here, and the bone is returned first. So to achieve a segmentation here, we can use any of the tools within the module. I'm going to use the Connect tool, which is available from Tools, Manipulate, Connect. And in the Connect tool, I'm going to use the Object Separator algorithm. Let's check the Object Separator, and I'm going to click on the right femur and the right hip, and then I'm going to click Separate Objects. Now this algorithm will go through and break away these objects from the main object, okay? And so we have the right femur colored as this red object, and the right hip colored as this green object. So let's rename these objects. So let's name the red object right femur, and the green object right hip. And we can click that. So we've partitioned the data into three objects. We have the original object, which is everything that's not been assigned to an object. We have the femur and the hip. So I'm going to save this object map, File, Save Object Map. I'm going to leave it with the default name, ct_pelvis.obj, and hit Save. So segmentation is actually done now. So I'm going to exit out of the volume render module, and I'm going to select the dataset and open up the surface extractor module. Now in surface extractor, the first thing I'm going to do is load the object map that we just created. So I'll select File, Load Object Map. Now the object map is overlaid on the grayscale image data here. So to do a surface extraction, let's hit Generate and then Extraction. That opens up the extraction parameters window. Because we have an object map loaded, let's click on Objects, and that will display all of the objects that are associated with our object map. I'm going to switch the original object off, and then the right hip off. And then I'm going to extract. I'm going to leave the default parameters as is, and just perform an extraction on the right femur. The extraction process will run, and it will report the number of polygons generated for our surface. So this is done to dismiss this, and I'm going to select the Save Surfaces option, and choose the location to save the surface. Let's name the surface as right femur, hit Save, and before we hit the final save, I'm just going to select a surface file that I wish to save this data set out in, the surface file out in, and I'm just going to select STL. And then I'm going to hit Save. Okay. So while we have the surface extraction window open, we may as well go ahead and extract the surface for our hip. So let's switch off the right femur and switch on the right hip, and then repeat the extraction process. Again, the process will run, and the number of polygons for the surface will be reported. We'll hit Done. Let's rename the file. We'll call this right hip, and then we'll hit save. So we have 2 STL files saved out to disk now, so let's take a look at these in our third-party software. For this demonstration, I'm going to use the free power view that's available from KitWell. With File, Open, and I'm going to select the right beamer and open it, then hit Apply to display this. So you can see the file has been rendered and is available for use in your third-party software. Now, if you want to load in the other files, just open them up, select the other file, and then hit Display. You may just need to pull back up the display here so we can see the entire model. Now, I exported 2 surfaces from our segmentation. There's no max here that you can pull out. So if we segmented the left hip, the left femur, the vertebrae, all of those could be displayed in our third-party software. So let's delete these, and we'll minimize our power view, and we'll go on to reviewing bone segmentation in MR, which is a much more difficult task than bone segmentation in CT. For CT, we just use threshold then, and the connect tool. In MRI, we're going to use a few other tools. So I'm going to switch to the MRI workspace. I'm going to click on the MRI dataset, and I'm going to use the volume edit module to achieve our segmentation here. Now, traditionally, bone segmentation in MRI is a very manual task. Typically, you'll have to go through slice by slice and do manual segmentation. With the release of Analyze 10.0, we added the volume edit module, which has a number of utilities to help improve and speed up bone segmentation in MRI. And one of those utilities is the ability to apply a silver enhanced filter straight off the bat to the image dataset. So let's go ahead and check that and put a filter to the dataset. And this filter can be switched on and off. But what it allows us to do is enhance the edges of objects. So you can adjust the edge strength. And I would refer to the boundary image. So I'm looking at the central view over here, and as I adjust my threshold range, my edge strength range, I want to make sure I've got a clear definition around the bone. Now, this edge that we're enhancing here will act as a natural boundary for segmentation. So let's say A4 is optimal, and it's going to be different for every data set, so you'll have to play around and see what works for your image data set. Now, I'm going to click on the center automated tab, and I'm going to select on Object Extractor. I'm going to add an object. I will rename this femur. We'll select a C point in the femur, and then we'll define a threshold range. So I'm drawing out a boundary, and anyone that's familiar with the object extractor process will know that we'll set a C point, it'll propagate through the slices, and it'll use morphological operations to erode, dilate, and try to detach that object from the surrounding objects. So we'll set a range here, and again, don't be too worried about the trace if it leaks out into other structures. We can define limits, just by checking limit, and then manually draw in a limit to stop that leak from happening. And again, we could probably draw a limit over here as well. But as I said earlier, we've also defined an edge strength, which will provide like a natural boundary to these objects. Okay, so we're going to extract object. The extract process will run, and once the process is complete, the femur will be rendered and returned in that upper left-hand window. Okay, so now. The segmentation is not perfect, but you'll appreciate if you've done any manual segmentation how long this would have taken if you were doing it manually to get to this point. So for a few seconds work, this is really good. You can use the manual tools to quickly clean up your image data. So we have the nudge tool here, which allows you just to delete regions which may have occurred outside of the target. So your choice may have leaked out. It can just be quickly cleaned up slice by slice. You can do this in the 2D image slices, or you can actually clean up on the 3D image. So if you select the trace tool, select the original object, and trace anything on the 3D image, that will wipe it out of the object. I'm going to click undo here. And I'm going to go back to the semi-automated tab, and I'm going to add a new object. And we'll go ahead and we'll do the tibia segmentation. So let's rename this object tibia. Again, we'll select the object extractor module utility, and we'll click the sort of C points on the tibia. So what I'm going to do here again is I'm going to adjust that threshold range a little here, just to roll that region out, and then I'm going to set a limit, just a rough limit here to stop this leaking again. Goes the silver enhanced algorithm has automatically put these boundaries around these objects. So let's go ahead and select extract object and see the result that we get. Once the process runs, the tibia will bend to the window. Okay, so again, pretty quick. You can rotate this, you can adjust this in 2D, you can again use the manual tools to correct for any regions that may have not made into the object, or any additional regions that may have been included or shouldn't be included. We could actually go in, maybe segment the fibula and the cartilage and generate tests to store those objects, but for the sake of time, I'm going to save the object map as is. I'm going to say that I'm happy with the segmentation, and we'll go ahead and we'll take a look at the different parameters that we can set, especially with tibia size, and see what effect that has on the femur. So let's save the object map. And again, I'm going to save this to our object map file. And then I'm going to close out